Ascension of the Celestial Maiden. Design and fabrication, fabrication and design. The site for this project is on the 11th and 12th floors of a 13-story residential building in Midtown Manhattan that has spectacular views of the United Nations and the East River. How to bridge 2 floors with ephemeral steel. The universal legend of the Celestial Maiden inspired the design of this staircase. Her spirit floats up to the heavens once she recovers the winding robe that she lost on the earth. How can we emulate her ascent in this staircase? Like the Celestial Maiden, this staircase must ascend to the heavens. We do not want to have a visible stringer. A visible stringer would spoil her ascent, her ribbon tied in knots. Then the stair needed to be cantilevered. However, in a typical cantilevered staircase, the risers are closed as structural support for the steps, ending up in a zigzag shape. Also, for the typical cantilevered staircase design, a long backspan is required to counter the load, and in this project we could not afford that space. The next apartment is right behind a 5-inch non-structural wall. Our idea was to bend the steps in the opposite direction. The steel can be folded to create a round, smooth, continuous edge as ephemeral as the ribbon. Our final goal is a continuous ribbon. Then how to achieve this? How to create this full openness? The cantilever is supported by the rigidness of the bent corners. There is no bracing which would disturb the transparency as you walk up. Let's open up the slab between the 11th and 12th floors. Shoring posts and beams are ready. The new steel beams were dropped on the sidewalk. This is Manhattan after all, and were carried up by hand through the small passenger elevator. The new steel beams were secured to existing steel beams. Be careful, right behind this wall is another apartment. The full folded strip was divided into several units and assembled. The step unit is attached to the stringer, which will disappear once the wall is built. The cantilevered steps project from a thick wall and look like they are floating. But wait! We have a glass handrail, which need to be attached to the steps. How to make sure that the side of each unit aligns perfectly with the glass. Unlike folded paper origami, thick and hard materials like steel may require a totally different technology, which would employ a computer-controlled laser cutter and special bending machine. 3D printers have become a buzzword, but 3D steel printers are not used at this scale of structural elements yet. If each module is composed from pieces combined through welding, controlling the edge is easy, but that sharp edge will kill the ephemeral impression of the smooth transition of the steps. The earlier idea to execute the concept was to cut out a long zigzag shape from large industrial-sized steel plate, using a CNC machine, and then fold it. A straightforward process. This process would create a lot of leftover waste, part of the nature of using a CNC machine. We would then need to bend that steel strip 24 times. Additionally, the location of the bending of 3/8-inch thick steel cannot be controlled very precisely. It is sort of unpredictable. Every bend accumulates the inaccuracy in the modules. The result is that the side of the module may be tilted or projected or set back from the others. The right-hand side of the unit is secured to the stringer hidden in the wall. The attachment detail allows for slight adjustment, but the accuracy of each module will directly reflect the alignment of the glass handrail. The glass handrail demanded this greater accuracy of alignment. Every unit can be identical, but the bending process is not very accurate. Instead, a foldable, wasteless, and superbly accurate method was developed using traditional tools. This accuracy was essential to accommodate the glass handrail, which did not allow for any tolerance. Before making individual modules, fold one large sheet just 4 times and slice it into 6 identical pieces. Identical units are automatically guaranteed. Stack them. The exact alignment of the glass attachment is easily achieved. This procedure resulted in precisely identical units, which would never have been achieved by bending the strips one by one. Let's start the real construction. The thickness and projection of the cantilever are calculated within subtle parameters, carefully engineered. If the units are too thick, the self-weight of the stairs will sag the cantilever. If it is too thin, it also sags, and it is not strong enough and will vibrate when you walk on it. This visibility transparency is essential for the Maiden to ascend towards the Manhattan high-rises. Her momentum is parallel to the direction of transparency. Oops, now she is descending. Finally, the combined 11th and 12th floors.